opportunity to speak here. So before I start, let me say that everything I'm going to be talking about essentially today is based on joint work with Giulio Stefani, who's also at MIT. So here's a brief outline of the talk. First, I'm going to introduce the motivating problem, which are these aggregation equations. And then I'm going to discuss the role of noise in studying these equations and specifically what our interest is. And then I'm going to formulate the problem that we're going to address, which is the effect of random diffusion on these aggregation equations. After that, I'll present the main results of our work with a few comments on them. And then I'll go a little bit, but at a high level, into the strategy of the proof, broken up into three sections: the local opposing step, the monotonicity step, and then, of course, putting everything together and concluding. And then at the end of my talk, time permitting, I'll leave you with some thoughts for the future about some questions and further directions of research. So for motivation, I want to consider the two-dimensional aggregation diffusion equation, which is given by 1, 1. So, okay, we just have partial t theta, we have this divergence, and then we have this quadratic nonlinearity here, where theta is some scalar, g is a potential, it's going to be the Newtonian potential on R2, and this asterisk is just denoting convolution. And then I have some diffusion term over here whose strength is determined by this parameter nu, which is greater than or equal to 0. So if nu is positive, this is just the parabolic-elliptic Patlak-Keller-Segel equation, which models the aggregation of cells by chemotaxis. But if nu is equal to 0, okay, we don't have any diffusion here. This is just a gradient flow with respect to a Wasserstein metric. And this models the evolution of vortex densities in superconductors, as well as has some applications to adhesion dynamics. So why am I interested in this equation? Well, let me explain. So let's just consider smooth solutions. And when I say PKS, I'm going to refer to just 1, 1. So I'm going to allow nu to be equal to 0 here. So they conserve mass. It's a short calculation to check that. So I can unambiguously denote the mass of the solution by m. And suppose I have some non-negative solution. Okay, theta is supposed to denote a density, so that physically makes sense. And I'm going to assume that it has finite second moment here. So you can check, just exercise an integration by parts, that if I take the time derivative of its second moment, I can compute that I get this expression over here. So what's special about this? Well, if the mass is larger than 8 pi times the diffusion strength nu, then this implies that the maximal time of existence for the solution theta has to be finite. And the reason for that is, okay, well, the second moment is a non-negative quantity. If this is negative over here, okay, then I'm decreasing at a strictly linear rate. And so eventually I'm going to have to be negative, which is a contradiction. As far as I know, this was first observed by some work of Jaeger and Lukaus in the 90s. So what are the implications of this? Well, if nu is equal to 0, this tells me that any non-zero sufficiently localized classical solution has finite lifespan. And in fact, there's a sharp bound for the time of existence of any compactly supported, which are necessarily unique, L-infinity weak solutions. And you also have explicit examples of finite time collapse to a non-trivial measure, as shown by some work by Bertozzi, Laurent, and Leger. And if nu is positive, well, okay, there's a unique global mild solution in L1, if and only if the mass is less than or equal to 8 pi nu. And in fact, you can say something about the asymptotic behavior as t goes to infinity, depending on whether you're in the subcritical regime where the mass is below 8 pi nu, this critical regime where you're at 8 pi nu, or the supercritical regime where you're above this threshold. And I've listed some names here who have investigated this. So, okay, this tells us that for this PKS equation, global existence is a non-starter for classical solutions if the diffusion is too weak relative to the size of the initial data. In particular, if we don't have any diffusion, then, okay, there's no global existence. We have finite time blowup. But in the past 2 decades, there's been a lot of research on understanding how adding some noise structure of varying forms to a deterministic equation can impact the behavior of solutions. And many people have investigated this. I've listed some names here. By no means is this intended to be exhaustive, so my apologies for any omissions. But concerning specifically these PKS type equations, I'm aware of two recent works. The first is some work by Flandoli, Galeatti, and Liu from this year, where they show that blowup is delayed, but not prevented or suppressed in a 3D version of this PKS equation on the torus, where you have multiplicative transport type noise. And there's this other work by Miziat, Stanishitsky, Topologlu, where they show that some random perturbations of this PKS equation lead to global existence for small mass initial data. So this isn't really too different than in the deterministic case, where we already saw that there's a mass threshold. I think the more interesting thing is that other perturbations lead to finite time blowup with positive probability for any initial datum. So as far as I know, though, none of these works have actually shown that noise prevents finite time blowup. In the interest of completeness, I'll mention that there are some works that show that you can suppress finite time blowup in these PKS equations if you have deterministic perturbations of certain transport type. But here we're not interested in these types of deterministic perturbations. I think the two works that are most relevant to our context are this work of Glattholz and Bicol from several years ago, where they looked at the 2D and 3D Euler equations, and they showed that by adding some linear multiplicative noise, in other words, some sort of random damping, this leads to global solutions with positive probability in Sobolev spaces. There's also some work, which I think is closest to our setting, by Buckmaster, Namad, Staffelani, and Widmeyer, where they showed that adding random diffusion leads to global solutions with positive probability for the inviscid SQG equation in these Gevrey-type spaces. And we'll come back to both of these works several times later on. But here I want to remark that, okay, well, SQG is the scalar equation, so may seem somewhat similar to this PKS equation, but a priori the dynamics are very different. SQG is a Hamiltonian flow, unlike the PKS equation, which is a gradient flow. And again, it's not a question necessarily with SQG that we know that finite time blowup definitely occurs. The long time dynamics of classical solutions is still in general an open problem. So motivated by these questions, these results in particular here, the question that I want to pose for today's talk is that, well, can one restore global existence of sufficiently regular solutions to the PKS equation by adding a suitable random diffusion? We've already seen at the very beginning that there's this mass threshold in the deterministic case that says that the diffusion is strong enough relative to the size of the initial datum, then I have global existence. What if this diffusion is somehow modulated in time by some noise structure? What can I still say then? So in order to investigate this question, and more specifically to answer it, I want to start not from PKS equation itself, but from a more general model of deterministic equations given by 1-3. So we have the same sort of structure as before, this divergence, this quadratic nonlinearity. But here I'm just going to allow M to be some constant d by d real matrix. And this is going to change the structure of the equation as I change M. And again, I'm going to have a gradient of a convolution with some interaction potential G. And I'm going to consider this on RD. So I've already told you what M is. There are several meaningful choices of M. If you take M to be anti-symmetric, you get a conservative or Hamiltonian flow. This corresponds to, for instance, the SQG case. But if you take, say, M to be minus the identity, then you get a gradient/slash dissipative flow. And this corresponds to the zero diffusion PKS equation that we saw at the very beginning. What am I assuming about the interaction potential? Well, very little. It's a tempered distribution. I'm going to assume that its Fourier transform of its gradient is locally integrable, and that I also have this decay bound. In other words, the absolute value of the Fourier transform of the potential G is bounded by xi to the minus gamma outside the origin, where gamma between 0 and d+1. Okay, so in particular, this allows for potentials in physical space that are very singular near the origin, but also allows for things that have long-range effects and actually may grow at infinity. So it's a very broad class. It's not a strong restriction. The model case, though, I think that you should keep in mind when you're thinking about this potential G is that it's a log or Riesz potential according to the following rule. So if gamma is D, that corresponds to a log potential. While if gamma is not equal to D, then I have this inverse power right here. And again, you could have a choice of sign. This would determine whether the potential is repulsive or attractive. And it's also somewhat useful to classify the singularity of the interaction relative to the Coulomb potential. So we'll say, for instance, that it's subcoulombic if gamma is above 2, it's coulombic if gamma is equal to 2, and it's supercoulombic if gamma is less than 2. This is kind of the opposite of what the terminology that's normally used, or it may seem the opposite. And this is because I'm working directly in Fourier space as opposed to in physical space. So I don't think I have to work too hard to convince you that this is a fairly broad and relevant model equation to start from. And there are many applications. For instance, starting in the conservative case, the most notable examples are, at least as I know, in 2D. And for instance, where M is, say, a 90-degree rotation, if G is just minus log X, or I guess strictly speaking, normally it has a constant here, so it's the Coulomb potential, then I just have the 2D Euler equation written in vorticity form, incompressible Euler equation. And as many of you may know, okay, we know local Wilposeness, actually global Wilposeness of classical solutions. This goes back to the 30s. And in fact, global Wilposeness for L infinity weak solutions by the Udovich theorem. And I'm sure there are further refinements of this that I'm omitting. If I, instead of gamma equals 0, I have this inverse power right here. Okay, this is just the inviscid generalized SQG equation. Gamma equals 1 would correspond to the usual SQG. And this is a geophysical model of a rotating stratified fluid. And this has been extensively studied over the years. You know that there's local Wilposeness of classical solutions. There's global existence of certain weak solutions. In general, they're not unique, though. And there's global existence of classical solutions if you add some suitably strong diffusion, as well as some examples of non-trivial global smooth solutions. But the important thing is that in general, unless there's been a major development that I'm unaware of, global existence is in general unknown for this family of equations. In the gradient flow case, there's even more applications. For instance, material science, cooperative control, granular flow, phase irrigation, lattice matter, swarming models. As far as I know, the Wilposeness is mostly limited to the model case of G that I displayed right here. And this is sometimes called a fractional porous medium equation. In the repulsive case, gamma equals 2. You have global existence, uniqueness, and asymptotic behavior. This is all known of non-negative classical and L infinity weak solutions. When gamma is, say, between 0 and 2, so you have a more singular nonlinearity, you have local Wilposeness of non-negative classical solutions, as well as some global existence, regularity, and long time behavior of certain weak solutions. But in general, these weak solutions are not known to be unique. In the attractive case, gamma equals 2, you have finite time blowup of non-negative L infinity weak solutions. I mentioned this result at the very beginning of the talk. You'll note that I kept saying non-negative here. If you, in the gradient flow case, if you allow for mixed sign solutions, the repulsive and the attractive distinction doesn't matter anymore. So that's why I was insisting on this non-negativity. So, okay, these applications and these may seem rather disparate, but perhaps a unifying perspective to keep in mind behind this model is that really this is a mean field model. It's an effective description for first-order mean field dynamics of the form 1-5. So you have a system of n particles, just given by evolves according to these ODEs right here. and you want to study its limiting behavior as the number of particles goes to infinity. And it turns out that the limiting behavior of these systems is effectively described by a solution of the PDE 1,3. Okay, so that's where these equations come from. And this has been extensively studied by many people over the years. So, okay, now let's come to the noise part. So we propose in this talk considering the following stochastic PDE. So I have my deterministic equation as before over here. And in the right-hand side, I'm going to add this diffusion term where I'm multiplying it or modulating it by white noise. And I can consider this on RD, where I have this inhomogeneous expression right here. Or I can also consider this on the torus, and I can drop the 1 over here. I have this homogeneous expression. The reason for this distinction is because if I'm in the periodic setting and I have this equation, then mass is conserved. So I can mod out by the mass and assume that I don't have a zero Fourier mode. And therefore, homogeneous and inhomogeneous Sobolev spaces are equivalent. But on RD, this doesn't quite work. And there are some technical issues at low frequencies that are addressed by making this inhomogeneous here. I'll circle back to this point a few more times during the talk. So nu, I'm going to assume it's positive. S is going to be just greater or equal to 0. I'll tell you some further restrictions later. And W is just a standard real Brownian motion. And importantly, this notation here is formal. As you know, you have to interpret the stochastic differential, but I'm intending this in the sense of an Ito differential. So if you were to write this in integral form, this would correspond to an Ito integral. And again, I want to say that we're going to focus on the RD case 1,6 as it's the more challenging, but everything applies to the periodic case, changing the things that need to be changed. So, okay, the first question is, how do we actually interpret this equation that I started with? This expression here is a priori formal. So motivated by these works that I mentioned at the beginning of the talk, Lutz Call and Buckminster et al., the idea is to transform this formal stochastic PDE into a random PDE. So what do I mean by that? Well, let's define a time-dependent Fourier multiplier, gamma t, where it's just this exponential right here, where W is the Brownian motion. And this makes sense for a fixed path of the Brownian motion. It's almost surely a locally Holder continuous process. So this is well defined. And then I'm going to set mu t to just be equal to gamma t applied to my solution theta t to this equation right here. Okay. So a formal application of Ito's lemma would show that the time derivative of mu satisfies this equation down here. So what's special about this equation? Well, okay, I can interpret this pathwise. I don't have any sort of stochastic differential appearing in the right-hand side like I did before. And by pathwise, I mean for a fixed realization of W, of the Brownian motion. And then perhaps more importantly, I've gained a diffusion term in this right-hand side over here, which is in contrast to the situation over here where I don't actually know that this should be regularized. Okay, this is white noise, Brownian motion changes signs. This is a very irregular expression. So, but after I've transformed to this random PDE, I can actually see this diffusion term. And this will be important to the mathematical analysis. And we're going to base our interpretation of our starting stochastic PDE on this random PDE 1,8. You may wonder why I chose the Ito differential over here to begin with. What happens if instead I have a Stefanovic differential? Well, you do the same sort of calculation. And remember that, the Stefanovic formulation is chosen to satisfy the usual rules of calculus. You wouldn't get a diffusion term over here. So this, having this expression just by itself isn't so helpful. So, okay, I think that concludes what I want to say in the introductory part. And then I want to shift to what we can actually say about this random PDE. So some preliminaries. I'm going to assume that I'm given some standard real Brownian motion and some filtered probability space satisfying all the usual assumptions. More importantly, I want to, given some parameters alpha, beta, nu, consider this following set. So I'm looking at the set of paths of the Brownian motion such that when I multiply it by nu, I stay below this function phi t. And what is phi t? Phi t is just this linear function. So I'm measuring, how large this new wt can go, or that it has to stay below this phi t. And I'm looking at the paths when it stays below this linear function here, uniformly in time. And you can open a probability textbook and you can figure out what the probability of this event space here is, and it's just 1 minus this exponential, okay? It's just an argument exercise using stopping times. So the other thing that I want you to recall, and this will be important to the function spaces that we use, are these Fourier-Lebesgue spaces. So I'm going to denote them by W hat SP. And so what is that? Well, I just take the Fourier transform of F. I multiply it by this factor here, a Japanese bracket in xi raised to the power of S. And then I take the LP norm of that, all in Fourier space. Okay. So as you may be guessing, if I'm using Fourier-Lebesgue spaces in this talk, I will be working, extensively directly in Fourier space. So what are the main results? The statement is a bit much to parse. So let me, don't try to read it yourself. Let me just try to explain it. So, okay, we're given some parameters here. The important thing is that gamma can be anything between 0 and d+1. That's the full model range of interactions that we started with. And that pretty much corresponds to, I think, the best you could expect if you wanted to have things that are still locally integrable. Okay, well, S, what is S going to have to be? In general, it's going to be between 1/2 and 1. S can't be too large. It also can't be too small. But in particular, it needs to be sufficiently large depending on gamma, which is the exponent that I have in my bound for the potential. And also, I need some integrability exponent R, which has to be sufficiently close to 1, depending on the parameters. In particular, you can always choose R to be equal to 1, and that's the most favorable situation. And again, I have one more parameter, which is sigma, and this just needs to be sufficiently large. So the important thing is that, okay, you give me some initial data, and I'm going to weight it by this Fourier multiplier right here, this exponential Fourier multiplier. And then I'm going to compute the Fourier-Lebesgue norm of that expression right here. And I'm assuming that this is sufficiently small, depending on this right-hand side. Beta and nu I'm given, and m, this absolute value of m, is just the size of the matrix that was in our equation. And c is some constant that you can compute. And I'm also assuming that I have a path, so an omega, a sample, in this good space here that I defined right over here. So for any such initial data in any path in this space, I have a unique global solution to my equation with initial data mu naught. And moreover, not only is the solution global, but in fact, I know that this quantity right here, if I look at its evolution in time, is actually strictly decreasing on the entire interval. So not only is it bounded, but we can actually prove that it's strictly decreasing. So, okay, sorry. I forgot that I split this into two. So here I'm actually assuming that gamma is between 0 and 1 in this statement right here. The second statement is that this is for the case where gamma is above 1, but still below d+1. And this is, again, the idea is the same. It's a little bit more technical, though. I need an auxiliary exponent q here, which has to be in this range, and I also need an auxiliary condition corresponding to this exponent q on the initial datum. But the statement is essentially the same. And the reason why the statement is more complicated in the case where gamma is above 1 is because this auxiliary condition corresponding to q is to deal with issues at low frequency when gamma is very large. And this is specific to the working on the RD case. If you were, in the periodic setting, then you could forget about this Q condition. Together, these theorems provide an affirmative answer to our motivating question that we started with. They show that adding random diffusion to these model equation that we began with, that includes the zero diffusion PKS equation, leads to global solutions in these Gevrey Fourier-Lebesgue spaces with positive quantifiable probability. And in particular, we're proving global existence of solutions for an equation that, without any sort of noise perturbation, necessarily blows up in finite time at these regularity of spaces. So some comments of the theorem. I didn't really tell you anything about the size of the parameters and the relations to one another. This can be made explicit. I don't think it's so enlightening to state that, so I'm not going to. If you're really curious, you can work your way through the proof. The more important thing is that what do I mean by solutions here? They are intended in the pathwise sense to this random PDE that I transformed to. And what do I mean by that? There's a good set of paths, this omega alpha beta nu that I defined before, such that for any path in this space and any such realization of the Brownian motion, I have a unique global solution corresponding to that realization. So if I do this, well, I can define a notion of a solution to my original equation, the stochastic PDE, just by undoing sort of the transformation. So defining theta t, and then undoing that gamma operator that I applied to begin with. And then you can show that you can bound the Fourier-Lebesgue norm of this theta t using the Gevrey norm of mu. But importantly, though, I'm not interpreting this original stochastic PDE in any usual sense, because I don't have solutions that are necessarily defined on the full probability space, so I can't make sense of that Ito integral. And again, I will circle back to this point. The second is that, or third, I guess, is that how you should interpret these results. Well, okay, you give me some alpha, epsilon, and nu, and some initial datum who's such that these two norms are finite, and we'll call this their sum E. So given this, you can choose a beta sufficiently small, such that with probability p, at least p, which is equal to this, there is a pathwise unique global solution mu with initial datum mu naught. And moreover, this Gevrey norm of mu is strictly decreasing in time. The other remark is that these theorems allow for initial data with arbitrarily large mass. The reason I bring this up is because at the very beginning, when we were considering the PKS equation, we saw that there was a mass threshold in the deterministic case for when you have global existence versus finite time blow-up, a mass threshold relative to the size of diffusion. But with these theorems, we can allow for initial data with arbitrary large mass. It's not too hard to produce examples for showing that. And again, I want to reiterate that if we're on the periodic setting and we replace this inhomogeneous Fourier multiplier with the fractional Laplacian here, we can omit this auxiliary Q condition, and you can just think about the setting of the first theorem that I showed you, where there's just this exponent R, no additional Q. Okay. And again, the reason for that is because of the conservation of mass and the equivalence of homogeneous and inhomogeneous Sobolev spaces in the periodic setting. So with that, I want to make a few comments on the strategy of the proof, beginning with just a high-level overview. So we're indebted to several ideas from these prior works by Buckmaster et al., and in particular, which itself drew on this earlier work of Glatz-Holtz and Bacall. And I think you can summarize the arguments in two main steps. The first is a local opposeness step, which in our case will be via contraction mapping argument. And the second case, or the second step, is to show the monotonicity of the Gevrey norm. And by that, I mean this monotonicity, I mean that the fact that the Gevrey norm was strictly decreasing as time is increasing. And that's going to be shown by an energy estimate. So what are the key difficulties here? Well, okay, the first is that you have these Fourier multipliers, gamma, gamma inverse, appearing in the nonlinearity. You may recall, this expression right here. These are exponentials. The Brownian motion is changing signs depending on what realization of it I have. So it's not a priori clear that you can absorb all of these Fourier multipliers appearing here. But again, that's sort of an issue that was encountered in prior work. I think what are really specific to our cases or become really challenging are the fact that we have issues at low frequency related to working on RD. These prior works just consider the periodic setting, which greatly simplifies it. But I think really RD is, in some sense, a more natural setting to consider this problem. Not everything in life is a box with periodic boundary conditions. And why this is problematic is because, well, I'm working directly in Fourier space, and I need to bound this gradient, the Fourier transform, or the gradient of the potential. But this may blow up as I approach near the origin, which is somewhat of an issue. The other issue that I want to highlight is that, okay, we have problems at high frequency stemming from the fact that this interaction G can be rather singular. I'm not really assuming much about it. And in particular, if I look at the gradient of the convolution of G with the scalar mu, well, this can be singular with respect to mu, as opposed to smoothing, for instance, in the Euler case, or of the same order in the inviscid SQG case. So, okay, what is the starting point? Well, the starting point is the local opposeness step, as you might imagine. So we need to show local opposeness for the Cauchy problem of the transformed equation, this random PDE right here. So, okay, it's some notation. It's convenient to write A to just be the square of this Fourier multiplier. And it's also convenient to introduce this time-dependent bilinear operator B over here, corresponding to the nonlinearity appearing here. We're going to rewrite this equation in mild form. And this suggests that we're going to solve this via contraction mapping argument. And to do that, we need some scale of Banach spaces in order to run this fixed point argument. And so that I don't have to keep saying it, I'm going to assume for the remainder of the talk that I'm given some alpha beta, and beta is sufficiently small depending on nu, and that my W, my Brownian motion, is always going to be a realization from this good set, omega alpha beta nu, that I defined before. And then I'm also going to use this notation Vt, which is this linear function given by alpha and beta, okay? So it's good to keep in mind these two facts, so the notation is not confusing. So, okay, what type of function spaces? I've mentioned this word Gevrey several times, and more specifically, I want to look at these spaces. I'll call them GA, kappa R. They have these three parameters, and these are Fourier-Lebesgue spaces, but with an exponential weight, corresponding to the square root of the operator A. So these are for functions which are static, but I also need some scale that's suitable for functions which are evolving in time. And so, okay, what you might guess, I'm just going to look at the functions which are continuous in time with values in these spaces G. And phi is going to be a time-dependent function, and I'm just going to take the supremum over all time, evaluate at this norm at fixed t. And again, this gives us a scale of Banach spaces. And some terminology, it's convenient to refer to A as, say, the exponential weight or the Gevrey index. Kappa is going to be our Sobolev index, and R is going to be our integrability exponent. Where do these spaces come from? Well, they're motivated by prior works on evolution equations where the similar L2-based spaces were used. But importantly for our setting, we need the freedom to actually take R arbitrarily close to 1, particularly as gamma is becoming closer and closer to 0. If you tried to work directly in L2-based spaces, I don't think this argument would work. You would get estimates which wouldn't close. In fact, you would get a restriction on gamma which scales linearly in the dimension, which is very prohibitive for large dimensions. As far as I know, and if somebody has seen these more general spaces in different contexts, please point it out to me, but I haven't seen the specific Fourier-Lebesgue variance before. So again, because there are issues at low frequency when gamma is large, we also need to have a more complicated Banach space, which I'll call it by X. And these have 2 parameters, or they're 2-tiered, I'll say. When gamma is small, it's less than or equal to 1, okay, you can forget about the second tier. It's just what I had before. But when gamma is bigger than 1, so when the potential, its absolute value, is singular near the origin in Fourier space, I need to look at the intersection with this auxiliary space and the corresponding Banach space for evolution equations. And the idea that you should keep in mind is that, okay, this R1 is going to correspond to the R that I always have, and I want R to be close to 1 because this is going to deal with the high frequency problems. But when gamma is large, okay, I need R2 to be something which is now large. And this is going to correspond to that exponent Q that you saw in theorem 2 more precisely. And that high exponent Q is going to be used to deal with issues at low frequency. Okay. And again, you can forget about this 2-tier structure if we work in a periodic setting and replace this inhomogeneous expression with the homogeneous fractional Laplacian. So these spaces satisfy 2 useful embeddings. The first is kind of trivial, but the second one it's not hard to show, but this is the one that's extremely useful. And what is this saying? Well, okay, you fix some A in kappa, and let's say that I'm going to also have an A prime, which is larger than A. And I have some kappa over here, and I have R. So you can ask what happens if I decrease the Gevrey index A prime. So I go from A prime to a smaller A. If you do that, well, then you can increase the Sobolev index kappa prime to be arbitrarily large. And again, R is just going to stay fixed. So by decreasing the Gevrey index by arbitrarily small, I can increase the Sobolev index arbitrarily large up to a constant, which is going to become larger as I increase the Sobolev index. And this fact that I can sort of lose an epsilon in the Gevrey index and then gain something in the Sobolev index is going to be really important to conclude the proof, in particular to access this monotonicity result that I'll tell you something about momentarily. So the local well-posedness, again, this is a bit of a mouthful. The important thing to take away is that we can find an R sufficiently close to 1 and a sigma that can't be too large. This is the important thing about sigma. A priori, it has to be smaller than this threshold, 2s minus 1 over s, such that I have a local solution in this, space x whatnot. Okay, so this is saying that I have a local well-posedness theory in some spaces where the Sobolev index can't be too large. And I need the integrability exponent to be sufficiently close to 1. And in particular, as gamma becomes closer to 0, I need to take R closer to 1. So you have the existence of a solution. We can quantify the size of its lifespan. And again, we have continuous dependence on the initial datum. Okay. And again, the important thing to remember is that a priori, this may be a local existence in a space which is rougher than the regularity of my initial datum. So at some point, we're going to have to reconcile the fact that I'm proving local existence in a space which is rougher than the regularity I claimed in the statements of my two main theorems. Okay. So I've already said all of these points right here. So I'm going to skip over that. Let me just make a brief comment about the idea of the proof. In caricature, you will need to estimate the Fourier-Lebesgue norms of these types of expressions here. So this is the nonlinearity written in integral form. I have this exponential weight coming from the definition of the Gevrey norm, and similarly the Fourier-Lebesgue norm right here. So it's convenient to make a change of unknown just by applying this operator and defining this new unknown rho. And using Minkowski's inequality and definition of this norm, it's not hard to show that this expression that I started with is controlled by this expression here. So, okay, now you've reduced to estimating this ugly expression down here. And I think the two important things to take away are the following. Well, the first is that we need to make sense of this exponential weight appearing right here. In particular, I have this noise, W, appearing here, and I somehow need to control that. Well, because I'm always assuming that S is less than or equal to 1, and then I'm assuming that my path is staying below this function, this linear function Pt, by choice of my realization, I can show that this exponent in the exponential is less than or equal to 0. And so then I can just bound this exponential factor by 1 and throw it away. Okay, this is a consequence of the fact that I'm working directly in Fourier space, and I have a good realization of the Brownian motion. The second thing that you should observe is that, okay, well, I have the diffusion coming from the structure of my equation, and I can use that to bound this other exponential by this decaying this exponential with a negative exponent. And you do all that, and you reduce to estimating this expression down here. And then, you can follow your nose. So you want to use this exponential decay to absorb factors of xi, which correspond in physical space to using the smoothing effect of the diffusion to absorb derivatives. And this will give you some factor of t to the minus tau raised to an exponent, a negative exponent, which I'm not going to write here. The important thing is that this the size of this question mark has to be less than 1 in order to get something which is locally integrable in time. To actually estimate these expressions, you need to do some paraproduct analysis and some Sobolev embedding. It's simplified by the fact that we work directly in Fourier space. And this is going to give you some conditions on all these parameters that I have floating around: R, sigma, S, gamma, the dimension, so on and so on. And then you need to do a bit of algebra. I think this is the most involved part to actually determine that you can satisfy all of these conditions simultaneously and obtain an estimate which closes. And the important takeaway is that smaller gamma means a smaller r and a larger sigma s. So in particular, the gamma is very close to 0. It would not work if I had r equals 2. I need to choose it to be close to 1. And in fact, if you just wanted to simplify your life, you could assume throughout what I'm saying that r is just equal to 1, which is the most favorable setting. So the next step is this monotonicity. And the idea behind this is that, okay, let's suppose we have a solution in one space here with two Sobolev indices, kappa r and kappa q. And let's also suppose that it belongs to this space over here with now two new Sobolev indices, kappa r prime and kappa q prime, which are larger than kappa r and kappa q respectively. So I have my function is also in a more regular space where regularity is measured by a higher symbol of indices. And I'm also assuming that my initial datum is sufficiently small, depending on a bunch of parameters. So if my original kappa R and kappa Q are big enough to begin with, then this would imply that this norm right here has to be strictly decreasing on an interval 0 to t. So in words, what this is saying is that the Gevrey norm of mu t is strictly decreasing on an interval, provided that we know a Gevrey norm with higher Sobolev index, but the same Gevrey index remains finite on the same interval. So, okay, this is good, but it's also a bit problematic because, I'm assuming that this result about being about being decreasing is conditional on having a higher regularity, which stays finite, which, a priori, I don't know that I have. So, to actually use this result to access the monotonicity, somehow one will have to deal with that. Hung, how am I doing on time?
Okay, you have 5.
5 minutes?
Yeah, 5 minutes.
Okay. So maybe I'll
10 minutes. Okay, 10 minutes.
Okay.
Okay.
So this is the actual rigorous statement of the results. I think I've said the important things, though. In words, again, it becomes more complicated when gamma is larger than 1, but the idea is the same. Here I'm assuming that my solution is in a more regular space, but its initial datum is smaller, sufficiently small in a less regular space. And then I'm showing that it's strictly decreasing. This norm is strictly decreasing, corresponding to the smaller kappa R. So again, in words, this is saying that this Gevrey norm is strictly decreasing, conditional on having a higher norm, which is finite. And by higher, I mean higher Sobolev index, but the same Gevrey index. So the proof really reduces to using the equation, the chain rule. You show this inequality right here. This first term is negative. Okay, that's good. This is corresponding to the diffusion structure of the equation. The second term, I'm just going to bound it by its modulus. And you need to show that the second term is not so large, then it cannot be absorbed by this first term, which is negative. And to show that, when again, use some paraproduct analysis and Sobolev embedding, this is analogous to the local opposing step. You obtain sets of conditions for these thresholds, kappa not R, kappa not Q. Smaller gamma implies that these need to be larger. And in particular, they're going to be a priori larger than the Sobolev indices in the local opposings proposition. So in other words, this monotonicity result is only for regularities which are above the regularity at which I'm constructing solutions to begin with. So somehow that's going to need to be dealt with. Okay, again, after you bound that nonlinearity expression that I had in the last slide, you arrive at this right here. So, okay, I have this stuff in parentheses, and then I have this factor right here. So this factor on the outside is corresponding to the higher Sobolev index, because I have kappa R plus 2 over R. 2 over R is positive. And then I have this expression inside the parentheses. So, okay, the second term down here is negative. And if I knew that this first term was smaller than this nu squared over 2 minus beta, then what's inside the parentheses would be negative. And if I knew that what's outside is finite, then I would be saying that the time derivative of this norm is negative. In other words, it's decreasing. So this is true at time equals 0, just by assumption on initial datum. And then using a continuity, also known as a bootstrap argument, you can conclude that it's also true on the full interval 0 to t. Again, so this is in caricature, it's more complicated I'm assuming if gamma is bigger than 1. Somehow I need to use the auxiliary condition for this exponent q. But the main idea is the same. So how do you actually conclude? Okay, well, simplicity, I'm just going to assume gamma is less than or equal to 1. The idea is that, okay, we have our initial datum to begin with. This is just as in the theorem. And we're assuming that this regularity sigma naught for our initial datum is above the regularity threshold kappa naught r given by the monotonicity proposition. And you also assume that the size of the initial datum in this norm is sufficiently small, depending on these parameters. C mon is just the constant given by the monotonicity proposition, whose dependence one can quantify. So, okay, local opposedness tells me that for some sigma small, I have a solution on some interval that takes values in g sigma r phi plus epsilon. The important thing here is that sigma is a priori less than the regularity of the initial datum and the regularity of this kappa naught r, which corresponds to the monotonicity proposition. So I have local existence of solutions in a rough space, and I have monotonicity in more regular spaces. So how do I use both of these results? Well, the main workhorse is this lemma here. And what this lemma is saying is that it's quantifying how much the maximal lifespan of the solution increases if I fix the Sobolev index sigma, but I decrease the Gevrey norm. So if I have two indices epsilon1 and epsilon2, and I have to look at the corresponding maximal lifespans of the solutions in these spaces right here. So BT plus epsilon2 corresponds to the lower Gevrey index. What this is saying is that if I decrease the Gevrey index arbitrarily, I am increasing the size of its maximal lifespan by a fixed amount, okay? The amount that I'm increasing does not depend on the relation between epsilon2 and epsilon1. And one shows this using a combination of this elementary Gevrey embedding that I showed you at the very beginning. This allows me to lose a little bit in the Gevrey index to go up to a high Sobolev index. And being at a high Sobolev index allows me to access the monotonicity result. And then by using an iteration, in particular the local opposedness proposition, and the fact that it gives us a quantitative lower bound on the lifespan of the solution, we can arrive at this inequality 328. And then once you have this, the actual conclusion of the main theorems, the proofs of the main theorems, I think follows fairly straightforwardly. I'm not going to write it. The main idea is a series of bootstrap arguments to work your way up to get the final result. But this lemma 3 is the workhorse. So with that, in the last couple of minutes, I just want to leave you some thoughts for the future, future research questions. The first is that, well, can you actually construct solutions that are defined in the entire probability space modulo some zero probability set? And I don't mean necessarily that the solutions are global on the full space. Wouldn't expect that, but that I at least have a notion of a solution that's defined for all omega, as opposed to just some omega. And why I think this is relevant is because in our current formulation, we don't really have a good interpretation of this original SPDE. I don't know how to write this in a usual weak form using an Ito integral because the theta that I get from undoing the transformation to a random PDE is only defined for some omega. So I don't know how to make the resulting Ito integral. And this limitation comes from the local opposedness step. I think by finding an argument that doesn't use the fact that it doesn't need this condition that this Brownian motion belongs to that good set omega, alpha, beta, nu. If you can do that, you can overcome this limitation. But this may require one to, use it. I don't think you could do this directly with the contraction mapping argument. Related to this is, okay, do you have to use Gevrey spaces? Can you use Sobolev instead? Sobolev spaces are what's used in the Holtz-Vakal work. The third question is, this is related to this connection to mean field dynamics I mentioned at the beginning, is that can you actually give us a microscopic derivation of these types of models with random diffusion in terms of a particle system? We can do that for other types of noise, but I'm not really sure how to do this for random diffusion. And then the most interesting question, I think, is that can you say something about the asymptotic behavior of solutions as time goes to infinity? We only know that they're global with high probability, but if you recall what's known, I mentioned this at the very beginning of the talk for the PKS equation, you'd ideally like to be able to say, how the solution is behaving as time goes to infinity. But at present, I'm not sure how to do that. And so with that, I'm going to conclude and thank you for your attention.